Let's do the Unit 5 progress check, free response question part A. And it says that there is going to be a twice differentiable function f. They gave us the value of the first derivative at 1 is equal to 0. Let's just stop and think about that for a second. We haven't read too far, but what we know so far is there's a function. We could take the derivative of it twice if we needed to. And that also implies continuity. Good to know. And the value of the derivative at 1 is equal to 0, which means we have the potential for a maximum or a minimum there. Where the derivative equals 0, we have maximums or minimums with the potential for it anyway. They gave us the value of the equation of the second derivative, and it's on this interval, so let's jump in. Part A. On what open intervals contained from 1 to 3 is the graph of f concave up? This one's pretty straightforward. I think we can get some easy points on this one. We'll type it in our calculator. Mine's already typed in, and we're going to graph this function, this second derivative actually, from -1 to 3. So we're going to press window, and we're going to go from -1 to 3. And we need to adjust our window accordingly to correspond to that. So we're going to press zoom and go down to number 0, just press 0 actually, zoom fit. That adjusts the y values automatically for the x value. So we have this graph we're looking at here. There it goes, there it goes. Okay, let's interpret what we're looking at. We are looking at the second derivative of a function. So that means, second derivative deals with concavity, that means that the function is concave down where the second derivative is negative. That would be from -1 to 0, maybe something crazy happens at 0, not sure, and all the way up to about 1 point something, and then from 2 point something to 2 point more something, we have some concave down, and then concave up from here to here, and concave up from here to 3. Okay, so the answer to the question is about concave up. I do want to make sure that nothing crazy happens at 0. I say nothing crazy. I have seen this before where they will do some sort of function that has, let me grab a scrap piece of paper really quickly. There it is. They'll do some sneaky little graph, and you graph it, and it looks like this, and you're like, oh, it doesn't cross the x-axis. But then when you zoom in, you like zoom in even more, and it does this little thing like that, and you're like, I don't know, and you zoom in even more, and then you see this, okay? So I just want to be careful about that. I want to make sure that we're not crossing the x-axis at 0. And actually, you could just plug in a 0 right here and realize that you don't. So if you plugged in a 0, you'd have 0 times everything else, and all of a sudden it's 0. So zoom in all you want. I just wanted to point that out. So let's find everywhere that the graph of f is concave up. That's from here to here, and from here to here. We have two answers, two intervals that we're dealing with. So second and calc, we're going to calculate a 0. That is where we cross an x-axis. We will do a left bound to the left of this point. We already are to the left of this point. We'll go to the right of that point, and there it is. 1.253, that's our first one. So number 1, part A, 1.253 to somewhere, don't know where, about to find out. Second and calc, 0. We're going to go to the left of this point. I'm sitting almost on that point, so let's go to the left of it. Go to the right of it. Guess. Just press enter on guess. Unless you have to cross an asymptote, then you need to be a little more specific. 2.171. And the other interval is from here to 3. So we could go ahead and put a 3 there if we wanted to. We know that much. Second calc, find the 0. To the left of it, to the right of it, and 2.803. Okay, there's part A. Let's read part B, see what happens. This one's going to be pretty easy as well, as long as we know how to interpret it. Does f have a relative minimum, a relative maximum, or neither at x equals 1? Justify your answer. Okay. Maximums and minimums occur where the derivative equals 0. Well, x equals 1 is where the derivative equals 0. Okay, so we don't know the function, and that's okay. But we do know that we have the potential for a minimum or a maximum. And we also have the value of the second derivative at 1. We're about to find out what it is, or we don't know, but we're about to find out. Let's go to the table, plug in a 1. We have a negative. So I'm going to write that down. Let's see. I'm justifying my answer right now. The graph of f has a relative. Okay, haven't even decided it. I've already started my sentence. When I have a function that has a derivative equal to 0, then we have the potential for maximum and minimum. We also have a second derivative that is negative. We just established that. Therefore, we have something that is concave down, and that means we have a maximum. Okay, so let's finish our sentence. The graph of f has a relative maximum at x equals 1, and I need to justify why. That is because, a couple reasons. We know that we had the potential for a maximum. Let's change this sloppy mess to a 1. There we go. The potential for a maximum at a 1 because they gave us that. And we know the value of the second derivative at 1, and it was negative. And because the value was negative, the graph was concave down, and therefore we have a maximum. We have said everything that we need to say. Now we get to the tricky one. Here's part C. Okay, this is where you really need to be creative. This is also where you need to skip it if you are stuck. You can earn some points on this, but don't spin your wheels on this one at the expense of the other ones, like part A, part B, even part D, which is pretty easy, I think, compared to C. So skip around if you need to. Here it goes. Part C. Use the mean value theorem. Stop right there. In order to use the mean value theorem, we have to have a function that is continuous and differentiable, because the mean value theorem says that, here's the visual for it, you have a graph, there is a slope that connects the endpoints, and somewhere from here to here on that interval, you have a point that has the same slope. Okay, that was a very rough representation. That's what just happened. Use the mean value theorem on the closed interval from -1 to 1 to show that f prime of -1 cannot equal 2.5. Whoa, what? Okay, first time I read this problem, I panicked a little bit, and I was like, they didn't give me enough information, and I was, revolting, not resulting. I was not getting results. I was getting revolts. Anyway, and then I realized that sometimes the best way to show something can't exist is to assume that it does and then disprove it. Here's what's about to happen. Follow my logic and then I'll start writing. We're going to use the mean value theorem. I'm going to doodle some thoughts before I get really formal with it. I'm going to use the mean value theorem and make the assumption that this is true, which means in a minute I'm going to go f prime of 1 minus f prime of -1 over 1 minus -1. I'm going to do that, and I'm going to get some number, and I don't know what it is, but that would be my slope for the derivative on that interval. Now, don't panic that you're not using the original. Again, when I originally read this, I was thinking, okay, mean value theorem means I need to do this. Not necessarily, okay? Because if I'm going to start with this, then eventually I'm going to say, well, the second derivative had better equal that same question mark, whatever it is, okay? And we're about to do that, and we're going to assume that this is true and then say, oh, no, actually it's not. So here goes. Follow me closely. Use the mean value theorem on that closed interval to show that f prime of -1 cannot equal 2.5. Well, let's just start with the assumption that it does. So the slope of the derivative from -1 to 1 would be given by this. I just wrote this on my scrap paper, and now we're going to formalize it here. 1 minus -1. We obviously have a 2 in the denominator. F prime of 1 is 0, they told us. F prime of -1 is not 2.5, but we're going to go with it. Well, if it's not, why are you going to go with it? Because in a minute, we're going to hit a roadblock and say, oh, wait, no, it can't. And that's what they want us to do. Okay? So minus 2.5. And that, my friends, is going to give us negative 2.5 divided by 2. That's negative 1.25, which means that somewhere on the interval from -1 to 1 for this differentiable function, it has to be differentiable, and it is, they said so. We'll put this in words in a minute. Somewhere from -1 to 1, the derivative of the derivative had better equal this. Okay? The process should look familiar. So here's what's about to happen. I'm going to start tinkering with the calculator and see if I can get the second derivative to equal negative 1 1/4. And if it doesn't work, I'll say, oh, wait, the whole thing fell apart. You know what? The derivative at negative 1 can't equal negative 2.5, or positive 2.5, sorry. So here we go. I have graphed the second derivative, and I'm going to also graph the line negative 1.25. I'm glad this one's calculator active. Actually, this particular piece of it could be done without a calculator. I'll explain why in just a minute. But if I was to graph everything I just graphed, there we go. The graph of the second derivative never crosses negative 1.25. They never intersect, not on the interval that we're dealing with. We're dealing with the interval from negative 1 to 1. Notice that they never intersect. Now they do over here, but we're not dealing with that. We're dealing with this. Okay? All right. So let's put this into words. I'm about to formalize everything that just happened and put it into words the best way I know how. Okay, for the mean value theorem to apply, we have to have differentiability, and we do. So since f prime of x is, let's get really specific, continuous, which is good. I'm going to get super specific, not of, is continuous on a closed interval, negative 1 to 1. So we can go from negative 1 to 1 and draw the whole thing. And it is differentiable on the interval from negative 1 to 1, open interval. The mean value theorem applies. So if f prime of 1, negative 1, was equal to 2.5, then there must be an x value on the interval, or in the interval, from negative 1 to 1, such that, okay, let's stop, pause for just a second. We just said the function is continuous and differentiable, so the mean value theorem works. Great. Because the mean value theorem works, we plugged in what we got. The second derivative should equal this. So there has to be an x value such that the second derivative equals negative 1 1/4. However, it's not. There is no number c. No number c. I use the letter c because that's often used here in this context. However, there is no such x value. So I don't know what the next letter was I was going to write. Maybe it was an F. I don't know what it was going to stand for. So actually, yeah, F. F prime of negative 1 cannot equal 2.5. So we basically went through the mean value theorem and said, hey, this must work. Oh, wait, no, it doesn't. So therefore, that original assumption is not true. There we go. That was fun. Let's do part D. That's a tricky one. That is totally tricky. Don't beat yourself up over things like that. You had the option, you had the availability of 3 points. Every free response question has 9 points available for it. This particular section had 3. Part C had 3 points. But you can get 6 points easily otherwise. Does the graph of f have a point of inflection at x equals 0? Give a reason for your answer. All right, let's graph. Here we go. We've actually already graphed it. We know what's happening. We've already talked about what happens at x equals 0. The second derivative bounces off the x-axis at x equals 0, so the answer is no. A point of inflection is where our concavity changes, and our concavity did not change because the sign of our second derivative did not change at x equals 0, so no. Here goes. Let's word it very well. F does not, underline it because we're angry, have a point of inflection at x equals 0, because I said so, no, because the sine of the second derivative, we'll put an x in there, probably should put it here too, not a huge deal though, does not change. There. There we go.